welcome to another video where we explore interesting physics question. This is actually from the same paper we did in the previous video, Cambridge Physics Paper 4, 2024, October-November, variant 4.3. So we'll start today with question 5b. Two charged isolated insulating spheres X and Y are near to each other as shown in figure 5.1. P is a point on the line joining the centers of the spheres. Okay. Explain why it is not possible for the total electric potential and the resultant electric field to simultaneously be zero. It's a very interesting question. Okay, let's first write the formula down. Electric field strength formula, Electric field strength formula is force per unit charge, or there's another formula where it's KQ over R square. Q is the charge, R is the radius, K is a constant, it's 1 over 4 pi epsilon naught. Then for electric potential, it's work done per unit charge. Another formula is KQ over R. The K is also the same constant. Okay, now let's start with drawing graphs. Okay, I'm going to start by drawing electric field strength graph. Okay, so we have our E here, we have our radius here. Okay, let's say this is a positive charge. Okay, now inside the sphere, within its sphere, within the radius of the sphere, the electric field strength is actually 0. Why? Because let's say you have a sphere conductor here. Okay, nice circle. Okay, so you have a lot of positive charges inside. What happens if a positive charge meets a positive charge? They begin to repel. So in this case, they will begin to repel equally to the side. They'll start to repel each other. Then, after that, it will actually become like this. All will start going to the side. So once they begin to repel each other like this, the net force will become 0 because they cancel each other out. Why? Okay, I give you an example. Let's say I have a box here. A person is pulling here at 6 Newton. Another person is pulling here at 6 Newton. What is my net force? Net force equals to 0, right? Because both will cancel out. Same thing in this case. All of them repel equally, causing the net force to be 0. When the net force is 0, the electric field strength will also be 0 because electric field strength equals to force per unit charge. Remember the formula we wrote here? So when the force is 0, your electric field strength is 0. That's why inside the sphere, your electric field strength is 0 within the radius itself. Then, after that, it will follow this pattern here. What pattern is this? This is where we follow the relationship of this formula. From this formula, we can deduce that electric field strength is inversely proportional to the square of the radius. So this part of the graph follow this relationship. We can sub in any formula, you will actually get this graph. So here, you probably have, let me pull this up. After the radius, at this point, after the radius, you will actually go and follow this pattern. Okay. Alright? Okay. Now, how about potential graph? Okay. Let's choose a different color so we can differentiate. Potential graph. This is our potential. This is our positive. FR here. This is our radius. Okay. How about potential? For a potential graph, inside the sphere, within the sphere itself, within the radius, it has a same potential throughout the sphere. Why? Let's look back at this diagram. Okay, realize that at every point, they have the same potential. In other words, it's not like this, where you have a lot of positive charge up and a little bit at the bottom. Then here you can say you have a high potential, and here you say a low potential. But in this case, it's not like that. They're equally distributed. So when they're equally distributed, the potential are the same throughout the sphere. That is why they have the same potential. Then you go down, pew, like a slide. Okay, this follows this formula relationship. Now, what is this relationship? Okay, this relationship, when I bring it here, we can deduce that V is inversely proportional to 1 over R. Am I right? So, this part of the graph follow this relationship. Okay, get the idea, right? Another important thing is electric field strength is a vector. That means the direction is very important. However, electric potential is a scalar quantity. But it is important to put in the positive and negative sign, which is actually from the charge, positive charge, negative charge. Do not get confused. These positive and negative are not direction signs, are not signs that indicate direction, are signs that indicate who does the work. Okay, let me explain. Okay, raise this. Alright. Okay, so if your electric potential is negative, it shows that the work is done by the electric field, or you can say work is done by the system, if it's easier for you that way. If it's positive, work is done on the electric field or system. Keyword by, keyword on. Let me give you a scenario. Example, we have two same charges. We have two same charges, and what they are supposed to do? Repel. But now, I want to bring them close together. When I want to bring them close together, I have to do the work. Work is done on the system. I have to do work on the system. I have to forcefully push them together. So when I do the work, when the work is done on the electric field or on the system, you will have a positive electric potential. Basically, a repulsive case will give you a positive electric potential because work is done on the system. Now, if let's say we have positive and negative charge here and negative charge, they will happily attract each other because opposite charge attract. So here you are not doing any work. The field itself will push them together because that is it's natural. It's natural, right? Because positive, negative, what they do in nature, they just attract. So work is done by the field. You don't have to do extra work to forcefully push them together. They will nicely go towards each other because they are attractive. So in other words, attractive cases are work done by the field. So your electric potential will give you negative. Okay, alright. Now, since we've got the concept cleared here, let's now look at two charges. Okay, this is electric field strength graph. What if we have two different charges? A positive one here, that's a negative one here. Okay. Same case, electric field strength within the sphere is 0. Electric field strength within the sphere is 0. Then here, it will go here, following the electric field strength inversely proportional to radius square. Same thing for the negative charge as well. Now, you might be thinking, why for negative charge I did not draw below? Instead, I draw at here. Why is that so? Okay. Remember I said earlier, electric field strength is a vector. So direction is very, very important. If you realize here, for this positive charge, the direction is this way. The electric field strength, the direction of electric field strength on the positive charge is that way. However, but for negative charge, it's actually inwards. Why? You might be thinking, why is it like that? Why has to go inwards? Why is it outward? Okay. Because electric field strength, right, is actually following the direction of force on a test charge. let's say I have a positive charge here and my test charge is usually negative. Not usually negative, sorry, usually positive. In the most case scenario, a test charge is usually positive. Positive here. What happened to my test charge now? Which direction of force will my test charge experience? This way. Why? Because it's repelling. That's why for positive charges, your electric field is outwards. How about for negative? Now let's say I have a negative here, my test charge is here. What will happen to my test charge? What will it do? It will attract. Am I right? That is why for negative, your electric field strength looks like this. Because electric field strength follows the direction of the force of the test charge. That's why here it's inwards and here's going outwards. Then if you realize, both of them in the end are following the same direction. So this is in the same direction. That's why we put all at one side. We don't draw one lower because it's not moving in opposite direction. This is not going this way. Am I right? It's going at the same direction. That's why we draw both of the sphere charges electric field strength on top. We don't have to draw bottom because it's in the same direction. Okay. So what will be a resultant electric field in this case? Your resultant electric field here will be this beautiful brown color I'm drawing. Here. And this is your field strength. Okay, let me erase the green color so you can see clearly. Okay, the brown color is actually your resultant electric field. Okay, this is electric field strength graph when you have two opposite charges. What if it's potential? Okay, how about potential? Let's look at potential. A potential graph. Okay, this is going to be a little bit different graph. Have a positive, have a negative. Okay, as usual, the positive graph is going to look like this. It's going to go down exactly the same as I draw on top. Okay, wait, let me draw. Alright, okay, it's not that nice, but you get the idea. Okay, alright, then for negative, this is where the difference come in. Negative, you draw it this way, in the opposite direction of the first one. Why? Because this is a negative charge. That means it gives you negative potential. And remember I said, for potential, the sign is very significant. It's very important because it shows who does the work. And it's important especially for calculation and doing your graphs. So since it's negative potential, we draw at the lower region. Positive, we draw on top. Now, what will be your resultant force? Okay, let's see. Our resultant force will look like this. Oops. Okay. Let me try to draw a nice one. Okay, why is this here and why is this here? I mean, why is it lower? You might be thinking, because when you take this line and this line here, when you combine them, plus them, you're going to get a bit lower because a line is lower here. And here, when you plus them, you're going to get a lower resultant potential when you add them. Okay. And at this point, if you realize, here is where your V, electric potential, equals to 0. Now, let's look at both of these graphs. Okay, let's analyze this graph and this graph. Here, there is a point in the graph where your potential is 0. And usually, it's exactly at the midpoint if and only if both of you have the exactly identical spheres. Exactly identical sphere, exactly same radius, then yes, you'll get exactly in between. The potential is 0. And here, you realize or not, there is no point on the graph where resultant electric field is 0. Now you might think, it's 0 here, what? However, look at where point P is. Point P is located here. It's not located in the sphere. It's located outside. So it has to occupy somewhere in between here. So, can you see there's no 0 there? So, it cannot be simultaneously 0. That is what the question is trying to say. Why is it not possible? Because for electric field strength, when you have opposite charges, you will not have any 0 electric field. However, when it's potential, electric potential with opposite charges, yes, there is a possibility. Not to say there is a possibility, you will hit 0 electric potential at some point. Okay. So what if we have two same charges here? This is electric field graph. Okay, we have a positive. I'm just going to let positive and positive be here. How will your graph now look like? Okay. Let's see. Okay, actually, this one is going to be a bit different. Okay, let's draw like this. Okay. Now, as usual, within the radius itself, it's going to have a 0 electric field strength. Then it's going to follow the relationship of E is inversely proportional to 1 over R squared. How about this positive? It will actually be downward here and go up this way. Now you might ask, why? Okay, let me show you. Positive here is going out. Right, your electric field strength. Here is also positive, it's going up. Is it in the same direction? Nope, it's in the opposite direction. In this case, it was in the same. Right? But for the case above here now, it's in the opposite direction. So if it's opposite direction, this thing you have to draw downwards now, because it's opposite direction, to show that it's opposite direction. What will be your resultant force? Your resultant electric field. This will be your resultant electric field. This will be your resultant electric field. Okay, let me erase the blue one so you don't get confused. Okay. This point, your electric field strength is 0. Can you see something? I feel like I saw this graph just now. You are absolutely right. You definitely saw the graph here. When you have opposite charges, your electric potential will have 0. You will have a 0 electric potential. When you have same charges, you will have a point where your electric field strength is 0. Now I think you can guess. What will be your potential graph if you have the same charges? You are going to get this graph. Okay, let me push this to the side. Oops. Okay, turns out I can't push. Never mind, let's just erase it. Okay, so, okay, draw a pink one here. You are going to get exactly the same graph as this. R, positive, positive. Within its radius, you're going to have a peak. The same potential, am I right? Then you're going to go this way, and you're going to go this way. What will be your resultant? Your resultant is this. The green one. Realize it is exactly the same as this. And it doesn't hit 0 at any point, if you realize. Doesn't hit 0. That is why you cannot have a simultaneous point where electric potential, not a simultaneous point, you can't simultaneously have electric potential and electric field, resultant electric field and total electric potential to be 0. Why? This is the reason. For you to have 0, you must have same charges and opposite charges together simultaneously, which is we know is impossible. You either have same charges or you have opposite charges. And clearly, based on the graph we draw, proves that it cannot be 0. You get the idea. So I think in exam, I believe it's best you draw graphs so you can see it clearly. Just a quick one. You don't have to go through the process I did all one by one, but just a quick one. When you have a positive charge, in two positive charge, what will the electric field strength look like? It's actually the opposite of each other, right? Now let's look at the answer scheme. Okay, what it says here. For potential to be 0, one potential must be positive and the other must be negative. The charges must have opposite sign. True? Charges must have opposite sign, which is correct. Opposite sign. Then only your potential can be 0. Correct. Exactly. For field to be 0, the field due to x and y must be in opposite direction. And they must have the same sign. If you see here, okay, let me erase a bit. If you see here, both have the same charges and both has opposite field sign. So, sign of charges cannot simultaneously be both same and opposite. This is what I said. You cannot have both same positive and negative at the same time. You cannot have positive, negative at the same exact time. Simultaneously, it's not possible. So, it is not possible. I hope you get a clear idea what do they mean by not possible, simultaneously cannot. Okay, I hope this video helps you to clear your mind, understand the concept. If you have any other question, please let me know in the comment. I'll definitely try my best to answer it. So see you in the next video. Have a nice day ahead. Alright, bye bye.